Okay, as I was saying, you can actually write the electron configuration of an element based on where it is in the periodic table. And personally, I think that's the easiest way to do it. That's the way I usually do it. Um, you can also look at the total number of electrons and basically start adding electrons to orbitals until you've used the total number of electrons using the filling order that you can get from that little chart we made a few minutes ago. You could do it that way also. And that's pretty easy too, actually. Um, one of the problems actually with doing it from the filling chart, the one with the diagonal arrows, is that each step of the way you have to keep in mind how many electrons each type of orbital can accommodate. So you have to keep in mind that the s orbital in any given shell accommodates 2 electrons, whereas the p orbitals in any given shell accommodate 6 electrons, and the d orbitals can accommodate a total of 10 electrons, and so on and so on and so on. The thing is, doing it from the periodic table reminds you about that, because you can see right here, this is the s block. You can see right there 2 electrons. There's the first s electron, there's the second one. You can see that there have to be only 10. Well, basically 10 is the maximum number of electrons in the d block because there are 10 spaces in the d block, and so on. So as an example, I chose the electron configuration of bromine to do. Bromine is right here, number 35. And to get to bromine, what we have to go through is, let me fold this so we can actually see it at the same time. What we have to go through to get the bromine, starting from hydrogen is in period 1. So this is 1s1, 1s2. So there's 1s2. Here's 2s2 right here. Then we come across 2p6. Come down to the next row, 3s2. Okay, 3p6. Come down to the next row, 4s2. Then we come to the d block, and you just have to remember that, though, for the d block, the n quantum number is always the period number -1. So these are going to be 3d, and there are 10 of them. We're past it, so it's going to be 3d10. Then we get to 4p. Now notice bromine is within the p block of the 4th period, so it's going to be 4p, 1, 2, 3, 4, 5. And you're done. That should be the electron configuration of bromine. And let me just check it against what I had before. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Yep, that's right. Also, if you look at the table, you'll notice that for bromine, the last previous noble gas would have been argon. So you can write the electron configuration of bromine as being argon plus whatever bromine has beyond argon. So this would be argon. What bromine has, well, argon has 18 electrons. So it's 2 plus 2 is 4, plus 6 is 10, 12, 18. So basically, it's the last previous noble gas plus the valence shell. The valence shell including all of the orbitals with the highest quantum number, or the highest principal quantum number, plus any d electrons in the n-1 level. So this is your valence shell. And so you could also write the electron configuration of bromine like this. So not too bad, actually. There are a few anomalies in the electron configurations. And they have to do with the stability of like half-filled orbitals versus having some that are half-filled and some completely filled. Um, so when we're talking about transition elements, we're talking about d orbitals in a shell whose number is period number -1. You would expect, say, just looking at the first row of transition elements, you would expect that chromium should end 4s2, 3d4, based on where it is. Because chromium is here, here. And if you look where it is, it's past the S block of shell number 4. So that's 4s2, 3d, 1, 2, 3, 4. So 4s2, 3d4. Pretty simple, right? Why isn't it that? What is it, first of all? Actually, it's 4s1, 3d5. And so what's happening is one of the 4s electrons is jumping up to the 3d level so that all 5 of the d orbitals can be half filled. So there is a bit of extra stability from having the d orbitals half filled. And it's enough to make it energetically advantageous for one of the s electrons to jump into the d orbitals so that all these d orbitals can be half filled. Okay, similar one occurs with copper. If you look at where copper is, copper should end with 4s2, 3d9. Actually, it's 4s1, 3d10. And that's because there's also some extra stability from having the d orbitals completely filled. Enough that it makes sense, energetically for that one electron to jump from the s orbital up to the d orbitals. And there are similar anomalies for the subsequent rows of elements in the transition elements. So the element right under chromium, molybdenum, should have a similar situation going on, except that the two n quantum numbers would be one higher. So it would be 5s1, 4d5, instead of what you would expect, which would be 5s2, 4d4, and so on. And also, similar things happen for the F block as well, where you can promote an electron up to a higher energy, what would seem to be a higher energy level, in order to get all of the F orbitals to be either half full or totally full. The F blocks, that's getting kind of outside what we really want to work with, though, so I won't go into detail about that. Well, okay, X. So now we can actually look at some of the lessons from quantum mechanics. And the chemical properties of an element are mostly determined by the number of valence electrons. And the reason the chemical properties in the periodic table are periodic is because the number of valence electrons is periodic. And so that's what's really periodic about the periodic table. Elements in the same column or group at least for the A groups, have the same number of valence electrons. And that means that they have similar chemical properties. And they tend to form compounds with the same formulas as each other. They tend to combine with other elements in the same ratio for elements within the same group. It turns out the noble gases are stable because all of the orbitals in all of the principal energy levels are full. And that's what makes them stable. And because of that, because having the same configuration or the same number of electrons as one of the noble gases makes an element really stable, what that means is the elements in groups that are close to the noble gases, or elements that are close to the noble gases in terms of electron configuration, are the most reactive elements, because it takes just a little bit to get to a situation where they're so stable. And so elements in groups with electron configurations that are close to the noble gases are very reactive. And that's because the noble gas configuration which means stability and low energy, can be reached with only a little change. So they really, really want to do it. Or sorry. And specifically the elements I'm talking about would be the elements in group 1A, which only have to lose one electron to get to a noble gas configuration. Those are extremely reactive. You know, you've probably all seen, if not in person, then at least on video, what happens when you toss some sodium in water. That's a pretty vigorous reaction there. The elements in group 1 are pretty, except for hydrogen, they're all really reactive and they're all pretty dangerous to have around. They're so reactive. That's because they only need to lose one electron to get to a noble gas electron configuration, which makes them very stable. So they really, really want to do that. The elements in group 7A, the halogens, like chlorine and fluorine, are also very reactive and kind of dangerous to have around because they only have to gain one electron to reach a noble gas configuration. So it's the elements on either side of the noble gases, in terms of atomic number, that are the most reactive at all. Elements far away from an electron, a noble gas configuration, are much less reactive. And some examples of those would be things like transition metals. Carbon is not very reactive, and things like that. Okay, there are periodic trends in a lot of qualities about atoms. Not all of them are actually chemical properties. There are some physical properties that have periodic trends too. And those are physical properties that are related to things like the structure of the atom or the number of electrons or the number of protons. Since those number of protons and electrons are periodic, then properties that depend on those will be periodic, even if they're just physical properties like size of an atom. For size of an atom, we generally use atomic radius. There are a couple different ways of looking at that. For atoms that are not bonded, but in contact with each other, they use what's known as the van der Waals radius. And for bonded atoms, that's referred to either as the bonding radius or the covalent radius. And the covalent radius, well, for bonded atoms anyway, probably shouldn't call it covalent radius for everything, but for nonmetals, it's going to be half the distance between the center of the nuclei of two atoms bonded together. Okay, for metals, that is just a pure metal, not bonded to a non-metal, but metals that are just like a chunk of metal. It's going to be half the distance between the center of the nuclei of two atoms that are adjacent in a crystal. And so there are a couple different ways of looking at it, but the trend would be the same for both. Just with some minor exceptions. So we're going to basically just not make much distinction between the two. Anyway, if you're looking at the periodic table, the atomic radius increases in going from right to left, and it increases going down a group. All right, so what that means in practical terms is that looking at a periodic table, for instance, it increases going from right to left. So lithium is bigger than neon, for instance. And it increases going down a group. So lithium is smaller than francium. The reason why the atomic radius increases going down a group is really obvious and really totally makes sense. It's because as you go down a group, you notice the period number increases. The period number is the number of the valence shell. So you're adding more and more complete shells of electrons onto the atom as you go down a group. It makes sense that the atom would get bigger. Something that looks, an atom that has, say, one shell of electrons is probably going to be smaller than an atom that has two shells of electrons, especially if they have the same number of valence electrons. And so that's basically why the atoms get bigger going down a shell or going down a group. Why they should get smaller going left to right makes a little less sense, because if you remember what going left to right in the periodic table means, it means each space you go left to right, you're gaining one proton and one electron and maybe some neutrons. But you'd think that if you're gaining stuff and going left to right, then the atom should be getting bigger, right? But you also have to keep in mind that the atom is mostly empty space. You've got the protons and neutrons crammed together in the nucleus, which is really small. And then you've got the really tiny electrons that are circling around the nucleus, but they're way far away from the nucleus. So most of the volume within an atom is nothing but empty space, literally nothing. And so what happens is that when you add going left to right, every time you add another proton to the nucleus, the positive charge on the nucleus gets bigger. And every time you add one more electron to the valence shell, the negative charge on the valence shell gets bigger. And a bigger positive charge and a bigger negative charge will be more strongly attracted to each other, and that will have the effect of bringing the valence shell in closer to the nucleus. And that pushes the inner shells closer in also. And what you're really compacting is just the empty space between the shells of electrons. So it's really easy to do. There's really no resistance to that. And that's why the atoms can actually get smaller even though you're adding more stuff to them, because you're basically compressing the empty space. That's the simplified explanation. The book, of course, goes into much more detail, and so we'll go over that too. But generally, if you remember that explanation that I just gave, you should be okay. What this means: that the alkali metals will be the largest element in any period. And the noble gas will be the smallest. Okay. One of the part of the explanation here depends on effective nuclear charge. And so this is when effective nuclear charge comes back. Effective nuclear charge is equal to Z minus S, which is actually the same as what I told you before, because Z is the actual nuclear charge which is the same as the number of protons, which is the atomic number. And S is the charge screened by other electrons. And in practice, what that means is the number of electrons between the nucleus and the electron of interest. Which is what I said before. That does not include any electrons in the same shell as the electron of interest. If the electron of interest is a valence electron, as it will be in most cases, then the number of electrons between that and the nucleus would just be the number of core electrons. So in most cases, S will be the number of core electrons, which is just all of the electrons except the valence electrons. So for example, for sodium, the atomic number is 11. Number of valence electrons is 1 because it's in group 1A. And so the number of core electrons would be 11 minus 1, which is 10. The effective nuclear charge is going to be 11 minus 10, which is 1 for a valence electron. Which just means that basically if you're talking about one of the first shell electrons, that is an electron that has nothing between it and the nucleus, then the nuclear charge that the first shell electrons experience would be the full 11. But by the time you get out to the valence shell, you got so many electrons between the valence shell and the nucleus that hardly any of that nuclear charge is left. And for this reason, the valence electron for sodium is not held very tightly. And sodium is easy to ionize. Or in other words, it's very reactive. For something like magnesium, the atomic number is 10. Wait a minute. Gotta check this. 12. Yeah, I didn't think that was right. The atomic number is 12. The number of valence electrons is 2. And the number of core electrons is 10. Z effective would be 12 minus 10, which is 2. for a valence electron. And that's held more tightly than for sodium. And that's why magnesium is harder to ionize and less reactive than sodium. Magnesium is still pretty reactive, but it's not nearly as reactive than sodium. Try it for something, say like one of the noble gases. So say for argon. Argon is atomic number 18. The number of valence electrons, it's a noble gas, it's in group 8A, so it has 8 valence electrons. The number of core electrons would be 10. And so the effective nuclear charge would be 18 minus 10, which is 8. That's really high. And so the valence electrons are held very tightly for a noble gas, and that's one of the reasons that they're unreactive. Because they really have a firm grip on their valence electrons. For the, so let's see, we're at 30 minutes already, so time flies. So we'll pick up with section 8.7 next time. So until then, see you later.